Okay, so we want to start with generating capacity reliability evaluation. And the first thing that we need to study is the model of the generation, right? Remember how we calculate the reliability of generating systems? We need the generation model, we need the load model, and then we'll convolve the two to get the risk model. Yeah. So we are starting with the capacity model or the generation model. So the determination of the required amount of system generation capacity to ensure an adequate supply is the most important thing. When you plan generating capacity expansion, what are you looking for? You say, hey, this is my expected load, so I want my generation to be this much, right? Obviously greater than the load. How much greater? That really is, again, whether you are doing a probabilistic study or you're doing a deterministic study, things like that, okay? So the total problem can be divided into two different areas. One is static capacity evaluation and the other is operating capacity evaluation. This is just like adequacy and security that I mentioned earlier, right? Because day to day you have operating capacity requirements, but in the long term you should have enough generation to meet the anticipated load demand, right? So that's what we call static capacity. So the static capacity relates to the long-term evaluation, whereas the operating capacity relates to the short-term evaluation, yeah? Hour to hour, day to day, how much do we need, what's happening if there's an outage, how do we replenish the system, and so on. So both of these areas must be examined at the planning level. However, once the decision has been made, the short-term requirement becomes an operating problem. You obviously need to cater to the operational problems even when you are planning the system. But once you have planned, you have your system in existence. If there is a problem, operational problem, you must deal with it, right? Because long-term planning cannot be done in a day. Long-term planning has been done for the next 10, 15, 20 years. So the operational planning problem becomes a problem when something happens which you did not anticipate earlier. So in this course, we will concentrate on static capacity assessment only. Yeah, we are not going to deal with operational reliability. That's another like couple of chapters in order for us to look at the operational reliability. The static requirement can be considered as the installed capacity that must be planned and constructed in advance of the system requirements. So again, we are looking at long-term planning. Okay. The static reserve must be sufficient to provide for these. When you are planning for the long term, you must make sure that you have considered the overhaul of generating equipment, the lifetime of generators, the maintenance of generators, the outages that are not planned, meaning the outages which will take place at random. So how do you plan for that? You need to have some data which tells you how often the generators are expected to fail, right? So a data collection scheme will always help. Otherwise, you have to just rely on your judgment. Finally, load growth requirements. You must estimate how the load will grow. And sometimes you must also account for load growth in excess of what you have anticipated. So in other words, you provide some redundancy. Yeah, you provide some extra reliability to the system. So one practice that has developed amongst utilities over the years is to measure the adequacy of both the planned and installed capacity in terms of a percentage reserve. I mentioned about this earlier. Yeah, this is a rule of thumb method, percentage reserve. And the drawbacks of this method are as follows. This tends to compare the relative adequacy of capacity provided for totally different systems. Yeah, percentage reserve 10%. If a system has 10,000 megawatt load, you say 10% reserve. Another system has 100,000 megawatt load, you say 10% reserve. What's the basis? Do we know the load profile? Do we know the generation profile? Do we know the forced outage rates of generators, the unavailabilities of generators? We don't know. So this percentage reserve method should not be used when we do probabilistic or stochastic planning. So this method does not attach any penalty to the generating unit because of size. And generating size does matter. A bigger unit will fail more often compared to a smaller unit. So you must keep that into account as well. Okay? So we are going to deal with the application of probabilistic methods to static capacity planning. That's going to be our focus now. So we want to consider, we are going to consider capacity planning to include partial or complete integration of systems, capacity of interconnections. So we are also going to be looking at whether our system is going to be interconnected with some neighboring systems, and then we can plan our capacity. Effects of unit size and design. As I mentioned, unit size does make a difference. We cannot assume that regardless of the unit being 1 megawatt or 1000 megawatt that they are similar. Yeah, they're actually not. In terms of outages, they're quite different. Effects of maintenance strategies, maintenance schedules must be incorporated in long-term planning, and any other system parameters, economic aspects associated with different levels of reliability. All this, where possible, should be considered in static capacity reliability evaluation. During planning, it is necessary to determine how much capacity needs to be installed, yeah, and how much reserve you need in the system. The ability to move the generated energy to bulk load points is not considered in hierarchical level 1, as I mentioned before. So we are going to assume that the transmission and distribution are fully reliable and capable of moving the generated energy to the consumer load buses. Okay, that's the inherent assumption in this paragraph. So how do we find the generating model? How do we describe the generating model? Generating capacity reliability is defined in terms of the adequacy of installed capacity to meet the load demand. Very simple. We say that we must have enough installed capacity to meet the anticipated load demand. But sometimes it may or may not happen, right? So what happens if there is an outage? Are you able to meet the load? Are you still able to meet the load? For example, you have 10,000 megawatt installed capacity and your load is 7,000 megawatt, correct? So one generator goes out, 1,000 megawatt. You still have 9,000, your load is 7,000. Are you able to meet, or do you need to redistribute the load? Do you need voluntary load curtailment? Do you need voluntary load curtailment? Do you need to use emergency measures like voltage reductions and things like that? So you exhaust all these options, voluntary load curtailment, voltage reduction, and even the connection from the neighbors, interconnected cables or transmission lines that you may have. You exhaust all those whenever we have outages. And after you exhaust those options, yeah, if none of that is enough for you to meet the load demand, then what do? Then you have a loss of load. You can't help it, you have a loss of load. Okay. Now, you may have heard of this willingness to pay and willingness to accept strategies. Have you? Willingness to pay and willingness to accept. So just now I was talking about reliability cost and reliability worth. I was mentioning about the interruption costs. So what happens in some countries, and I'm not quite sure if it happens here, I'm sure it possibly does. The utility will go to the customer, usually big customers, and say, hey, I'm going to cut off your supply for this long on this day. Are you willing to accept that outage? For that, of course, the company will pay, will pay him. So that is called willingness to accept. The other one is willingness to pay. So the consumer says, no, I'm not willing to accept that. Yeah, I'm willing to pay you, but please let my power be on. Yeah, I'm willing to pay you more. So there is these theories these days, willingness to accept, willingness to pay. But whenever there is a loss of load, then none of this works, because you have exhausted all the possibilities, including willingness to pay and willingness to accept. So the definition of loss of load means you have exhausted all the possibilities, voluntary load curtailment, voltage reductions, interconnection benefits, willingness to accept, willingness to pay, and now you have no choice but to cut the load. So the definition of loss of load means the capacity that you have in your system is less than the load. So the load is 1,000, the capacity is less than 1,000. You have to cut the load. So that is how we define loss of load. Yeah, so it's very important for us to recognize the definition of loss of load. So the basic methodology will be to develop a model for generation, develop a model for load, and then to combine the two models. So we can repeat that calculation for weeks, we can repeat it for months, we can repeat it for years, yeah. And depending upon the load model, are we using the hourly loads? Are we using the monthly loads? Are we using the daily loads? Yeah, so accordingly we will be able to get the reliability indices and so on. So the probabilistic criteria that we use for generation system reliability and the most popular indices, I just want to elaborate first before we look at how we calculate these indices. So some of the most popular indices are these two, loss of load probability and loss of load expectation. So what is the loss of load probability? You look at those words, loss of load probability. So it's the probability of loss of load. Nice and easy. So whenever there is load cut or whenever there is loss of load, what is the probability that that will happen? That's called LOLP. It's a probability. So I tell you LOLP is 0.9 and you say, what the heck is that? It's a probability. So the disadvantage of this probability is that it does not tell us the severity of the situation. How much load are you losing? Your loss of load probability, I say, is 0.9. Are you losing 1 megawatt load or 10,000 megawatt load? Doesn't tell you anything. Are you not supplying 100 megawatt hours of energy, or are you not supplying 1 gigawatt hour of energy? Doesn't tell you anything. Just tells you the probability that load will be cut. So inherently you say, hey, that's not very meaningful to me. So we look at another index called the loss of load expectation. Now this one is slightly better. Why? Because it tells you the number of days or hours on which the load will be higher than the available capacity. Meaning, whenever there is loss of load, how many hours or days are we losing power? So it's a little bit more intuitive, but hours per year, that's the, you may remember, sir, 0.1 days per year. I used that 2 days ago. That is the most benchmarked index for LOLE in North America, North American utilities. 0.1 days per year, 1 day in 10 years. And if you of course try to put it in hours, 24 hours in 10 years, 2.4 hours in 1 year. Yeah, 2.4 hours. Of course it doesn't tell you whether I'm going to lose 2.4 hours on 31st of December or whether I'm going to lose 0.1 hours in January, 0.2 hours in February. So it could be, right? We know nothing like that. We don't know the frequency. We don't know the duration. All we know is how many hours per year are we not going to get supply. Is it enough for us? Well, doesn't matter. It is the most popular index at the present time. Now, interestingly, when we say that it is hours per year or days per year, hour is time, years is time, right? Can I not convert hour to year so it becomes year by year? Or can I not convert the denominator year to hours, then it becomes hour by hour? What is hour by hour? What is year by year? Isn't it a probability? So actually these two are related, the loss of load probability and the loss of load expectation. Yet this is more popular because at least we can relate to that number. We can say, oh, 5 hours per year. Yeah, I can see that. Although I don't know whether that 5 hours will be just a one-off or it will be like 10 times stretched over, different durations. Even though I don't know that. That only happens with the frequency and duration indices like I mentioned yesterday. We as customers want to know how often will we have power outages, and whenever there is an outage, how long will it last? That's the duration, right? So those are most meaningful to us, but calculation of those indices is slightly more complex. That's why this is much more popular, loss of load expectation. The next one, loss of energy expectation, sometimes also known as expected energy not supplied or expected unserved energy, EUE. I mean, different acronyms are used in the literature. Don't worry too much. In layman terms, how much energy is not supplied whenever there is loss of load. Yeah. So as the name indicates, clearly we are looking at loss of energy, whereas in the LOLE, we are looking at loss of load. So that's the fundamental difference. Obviously, this should be more meaningful, right? Energy. I mean, these days we have energy limited systems. Our solar systems, our wind systems, our geothermal systems, they're all energy limited. In the past, we didn't have those. So everything was capacity limited. Now we have not only capacity limited, we also have energy limited. So actually this index should be more meaningful, and it is getting more popular with time because of the energy limitations in our capacity building. So the other ones that are also used, EIR, Energy Index of Reliability, and of course its complement, Energy Index of Unreliability. So if I know this, then I know this, and vice versa, because they are each other's complement. So energy index of unreliability is 0.00001, then energy index of reliability is 1 minus that. So it will be a string of 0.9999, things like that, okay? So why do we need these? Because sometimes you have got two systems, yeah, and you want to compare them on a, what we call an equal footing, yeah, rather than, you treat them as completely different. So you normalize the loss of energy expectation by the total energy demand. And therefore you can compare system A with system B with system C when we normalize with their energy demand. Because system A, the energy required may be only 1 gigawatt hour. System B, the energy required may be 1000 gigawatt hour. So are we comparing apples to oranges? Yeah. When we look at only LOEE, we may be, right? So this helps us to normalize the energy not supplied divided by the energy required, energy demand of the system. That helps us compare different systems across the board quite nicely. Then F&D, we already mentioned this, the frequency and duration indices. Unfortunately, because of the need for additional data, yeah, so this one is not as popular. And last but not least, this is another index that the North American power utilities use. It's called SM, System Minutes. Yeah, anybody heard of that before? System minutes. It's a very interesting index because this says loss of energy expectation normalized by the peak demand instead of the energy demand. Normalized by the peak demand, yeah? So what will you get? Megawatt hour energy not supplied divided by peak demand in megawatt. So what are the units? Hours, right? And then of course you can convert hours to minutes. So it's called system minutes. So what's the reference? What's the threshold? In North American system, the number that they use is 25 system minutes. Yeah, just like that 0.1 days per year, 25 system minutes. So just to put this in perspective, what do we mean by that 25 system minutes? Yeah, it means that it's not a real time. It means that this would have been the annual outage time if all the energy interruptions only occurred at peak load. I hope you get the gist of it. So when I say 25 system minutes is a good reference, the system should not exceed 25 system minutes. What does it mean? It means that it would have been the annual outage time, 20 hours, 30 hours, whatever is the annual outage time. Unavailability, remember? Unavailability is the annual outage time. If all the energy interruptions only occurred at peak load. So whenever there is a loss of energy, it is occurring at the peak load. Of course, that's not all the events where energy loss takes place. But if you consider that that's the extreme situation, then the system minutes will contribute towards that number, 25 system minutes, okay? Usually, of course, as I said, in reality, it is much greater than the reference or the threshold that is specified in the literature by utilities. So I must re-emphasize to you that all these measures are expectations and they are not deterministic values. And of course, when they are expectations, they are described by a probability distribution. That's why yesterday we studied the exponential and normal distribution so that we can relate to, hey, okay, this is the mean of that distribution, but this is not everything, right? So they provide valuable indicators of the performance of the system, taking into account stochastic characteristics and even deterministic characteristics of the generation system and the customer load demand. So now we are at a stage where we can start to look at the generation system model. And this model is very, very commonly used by utilities almost throughout the world, but mostly in the Western world, at least that I'm familiar with. Yeah. And before we talk about the model, I want to introduce you to some key words. What are those key words? Generating unit. What is a generating unit? We use that loosely to say a generator. But what does it comprise? This is an IEEE definition, by the way. Generating unit means all the equipment up to the high voltage terminals of the generator and the station service transformers. Everything included in that is called a generating unit. So when you hear me say generator, please know that I'm saying generating unit, okay? Because it's easy to say generator rather than generating unit all the time. It's much longer. Then what is a forced outage? That's the other definition that we need to know. Forced outage means the occurrence of a component failure or any other condition which requires that the generating unit, this generating unit, be removed from service either immediately or up to and including the next weekend. If you can't remove it immediately because maybe it's dangerous to remove it out of service immediately, yeah, maybe things will go out of sync totally and things like that. There must be reasons to do that, but it must be removed by the very next weekend. So if the outage takes place on Monday, then by Saturday you must remove it, if not immediately. That's the definition, IEEE definition of forced outage. So for the generating unit for us, we are going to define a basic generating unit parameter which we use in the generating capacity reliability evaluation. And that is the probability of finding the generating unit on forced outage at some distant time in the future. Remember, we are doing static capacity reliability evaluation, long-term planning. So we want to know at some point in the future, what is the probability that the generator will be up? What is the probability that the generator will be down? Yeah, that's what we are after. And this particular parameter is known as generating unit unavailability. Yeah, usually it is a very small number. That means that the generator is highly reliable or highly available. And for some reason, it is very popularly also known as the forced outage rate of the generating unit, FOR, forced outage rate. Now, strictly speaking, the unavailability cannot be a rate. Remember the unavailability? Remember the equation for unavailability? Unavailability is lambda over lambda plus mu. Availability is mu over lambda plus mu, correct? So, lambda is failures per year and denominator is failures per year plus repairs per year, right? So, normally it's not a rate, yeah? And yet, this is the other way to describe that unavailability. Normally, it's just a probability. It's not a rate, yeah? But somehow, somebody came up with this and nobody has questioned that it is not a rate. It's very popularly used as a substitute for unavailability, okay? So, what is the forced outage rate? When you see FOR, it means forced outage rate, which is the unavailability, as I mentioned, is equal to U because we have used A for availability, U for unavailability. So unavailability is lambda over lambda plus mu, and of course we know lambda is 1 over m, and we know mu is 1 over r. Remember that? Where m is the mean time to failure and r is the average outage time or the mean time to repair. MTTF, MTTR, MTBF, if you combine the two, mean time between failures, right? So this is also written as total downtime. R, what is R? R is downtime divided by downtime plus uptime. Mean time to failure is also the uptime, isn't it? Usually, if you recall, in our discussion, we said mean time to failure is very large and mean time to repair is very small. That's why sometimes the mean time between failures is equal to the mean time to failure because MTTR is so small, right? Especially for electronic components, we don't have repair, yeah, because once a component fails, it's out the window anyway, right? So downtime over downtime plus uptime, that's how the unit availability is defined as the probability, the availability is the complement of unavailability. So it is defined as the probability of finding the unit in the operating state at any time in the future. Unavailability is the probability of finding the generating unit in the failed state at some distant time in the future. So they are each other's complement, assuming that the generating unit can only exist in two states, up or down. We'll see very soon that it need not be that way. So availability is mu over lambda plus mu. It is the total uptime over total downtime plus uptime. So you must be familiar with all this terminology. Lambda is the expected failure rate, mu is the expected repair rate, small m is the mean time to failure, small r is the mean time to repair, m plus r is the mean time between failures, f is the cycle frequency, t is the cycle time, right? We already went through this, I believe, sometime yesterday, so shouldn't catch you by surprise. And this concept is applicable only to a two-state unit, as I was just telling you. So the generator is either operating or it is failed. It can go from the operating state to the failed state by this transition rate called lambda. And once it is failed, you will try to repair it and bring it back to the operating state by this transition rate called mu. Now this model is applicable to the base load generating units. So good examples are nuclear power units, hydropower units. They are good base load power units. You just put them to meet the base load, yeah. Whereas when you use generators for peak shaving, for shaving the peak, then it's a different model. You can't just use a two-state model because they are intermittently starting up, shutting down, starting up, shutting down. With the base load units, we don't do that. Once they are up for several months, if not years, right? So base load model, base load unit model is different than an intermittent load unit model. So we can also model the generators using this three-state model. I've mentioned it many times that researchers have actually gone up to 13 to 14 state models, and they figured out that we do not need to model the generators by that large number of states. Instead, we can collapse all the intermediate states into one state called the partial output or derated state. So we've got this model. Remember, the most important thing is very easy for us to appreciate this here. But do I know lambda? Do I know mu? Do I know this lambda 2, mu 2? Where are these numbers coming from? If we don't have enough confidence in the transition rates, we will never be able to arrive at the correct availability or unavailability of the generating unit or of the system. And therefore, our risk in the system may be completely off, right, than what we should be getting, correct? So the data is so very important. For this particular purpose, we are assuming that we already know the lambda and the mu, but that's a bigger question, right? So this is the three-state model where we have a partial output or derated state. We can use that, and a little later I will show you one numerical example where we have the derated state as well. So the two-state model does not adequately represent a peaking unit, as I mentioned just now. So the IEEE has come up with this model, the four-state model for a peaking unit or a unit which works intermittently, doesn't work continuously. It's used only for peak shaving, usually for short periods of time. So you can see here there is a probability of starting failure that's also included, yeah. PS is the probability of starting failure, because whenever you are trying to turn on this unit, it may fail. Yeah, that's called probability of starting failure. So usually these are the gas turbines and some of these units which are used intermittently for peak shaving. Yeah, they're not the base load units. They're always typically the gas turbines. So anyway, we will not be using this four-state model, but I want you to know that if there is peak shaving being involved, then you should actually use this model. But of course, you need to know what is D, what is T, what is PS. You need to have all that data again. Everything boils down to the data. If we don't have the data, we are using a much complex model than what we should be using. Okay. So now we are ready. We have defined a generating unit. We have defined a forced outage. We have defined a generating unit unavailability, generating unit availability. We have defined a 2-state model, and we have also defined a 3-state model. The 4-state model for now we'll not consider, which is used only for peak shaving. So how do we build the generation model? We are going to build the generation model in the form of COPT. It's called the capacity outage probability table. Now look at those 4 words: capacity, outage, probability, table. So what does it tell you? That it is a table. It is a table of what? Capacity outage probabilities. So it's a probability table showing you the various capacities on outage. So very simple, capacity on outage, the corresponding probability, that's what it is showing us. So we will be able to get through this table what are the various ways in which the generating unit will fail and what are the corresponding probabilities of those failures. That's all. So this is a very, very useful model for the generation. It's called capacity outage probability table. It's just an array of capacities and probabilities, as you shall see shortly. But before we do that, we must make sure that we know what the assumptions are. Whenever we do these studies, we must be clear what are the assumptions we are making. So we are assuming that each generating unit consists of only 2 states. It is either operating or not operating. Multi-state models can also be used to represent the derated states. And there is one example later on where I'm going to show you how we use the 3rd state instead of just a 2-state model. Okay? That's one assumption. The second assumption is the failure performance of the unit is independent of the operating level, the system load, and the outage pattern of other units. What does it mean? In our terms, we have been saying that the generators are independent. One generator outage is independent of another generator outage. There is no common cause. Yeah, we have something called as common mode failures, common cause failures. So here we are ignoring them. We are saying that the outages are independent, completely independent. Okay. So generating capacity out of service due to forced outages is multinomially distributed. Can be binomial if the generators are identical, but if they are not identical, then you will find that it is not binomial. And the total number of states, capacity states, is 2 to the power of n. For example, if I've got 2 generators, each generator can have only 2 states, up and down, then the total number of states is 2 to the power 2, which is 4, correct? If I have 3 generators, it is 2 to the power 3, which is 8, and so on and so forth. So these are the states for a 3-generator system. Yeah, all 3 are up, C is down, B is down, A is down, and so on. And I think a picture is always worth 1,000 words. I can keep talking until the cows come home, but I think you can visualize from this picture a lot better. So 1 up, 2 up, 3 up, and then 1 fails by its failure rate lambda 1. So I have 1 down here, 2 is still up, 3 is still up. While you are trying to repair one, yeah, then 2 fails. While you are trying to repair one and bring it back here, 2 fails. Okay, that's what it means. Or 3 fails, right? So all these rates can be included in this 8-state Markov model. This is a 8-state 3-component Markov model of the system. And you can see all these transitions here. This is all the 3 are available. This is all the 3 are unavailable. Yeah. So the basic statistic that we will be using is the generator forced outage rate. I already told you what is forced outage rate. It is also known as the generating unit unavailability. Okay. So we are going to start with a simpler case using the binomial distribution. And of course, we have seen the binomial distribution earlier, yesterday or before. The probability of our outcomes is equal to NCR U to the power of R, A to the power of N minus R. A is the availability, U is the unavailability, N is the number of identical units, R is the number of units in the failed state, if you define that failed state is your outcome, and PR is the probability of R units in the down state. So using this distribution, we can find P0, P1, P2, P3, P4, etc., right? So let's look at an example. We are starting with binomial, and later we will see that there is a recursive algorithm where we don't have to rely on binomial. Why? Because most units in a power system will not be identical. Yeah, they will be non-identical, so we cannot use the binomial. But if you have systems where the units are identical, then this is very, very useful. So let there be 4 identical generating units, each 25 megawatt, and the forced outage rate is 1% for each of them. So the probability of 0 units in the failed state is 4CR, remember NCR, U to the power of R, and A to the power of N minus R. So you just put those numbers in, you find that this is the probability that 0 units are in the failed state. Obviously you expect that to be very high, isn't it? If all the 4 generators are quite reliable, and they are, forced outage rate is only 1%, that means their individual reliabilities are 99%. So the probability that none of them is failing is 0.96. Similarly, the probability of exactly 1 unit failing is 0.0388, and so on and so forth. Obviously, if you add all the probabilities, they must add up to 1, because you have exhausted all the possible outcomes. 0 failure, 1 failure, 2 failure, 3 failure, 4 failure, because there are 4 generators, right? So now we look at this table, which is called the capacity outage probability table, COPT. This is what it looks like. I say that there are 5 states here, so I call it I. Capacity that is available if I am in this state. If the capacity out is 0, then capacity available is 100, isn't it? 25 megawatt times 400 megawatt installed capacity. So capacity in, capacity out, state number 1, state probability 0.96. We found this, right? When no unit is out. Yeah, so that's what it is. 100 megawatt available, no unit is out. This is the state probability. State probability. I repeat, very soon I'm going to show you something else called cumulative probability. Yeah, which is slightly different. Oh, actually it's here. It's right here. So cumulative probability is written as uppercase P. State probability is written as lowercase p. Please see clearly, okay? So what do I mean by cumulative probability? Is the capacity on outage equal to or greater than the indicated amount. Equal to or greater. So I've given an example. Cumulative probability of 0 megawatt or more than 0 megawatt on outage. What is it? Cumulative probability of 0 megawatt out or more than 0 megawatt out. It includes everything, right? 0 out, 25 out, 50 out, 75 out, 100 out. So basically that is this probability, right? Has to be 1. Yeah, it includes all the possible outcomes. So cumulative probability of state 1 will always be 1. And then you can go down this table. 1 minus 0.96 will give you this value. Okay, I'm just telling you how you can arrive at the cumulative probabilities. The first one will always be 1. The second one will be 1 minus this value. The third one will be this minus this value. The fourth one will be this minus this. Fifth one will be this minus this, until you get to the last value, which will be the same as this. Okay? So we can derive the cumulative probabilities from the state probabilities. Alternatively, maybe you find that easier. You add this plus this, you'll get this. You add this plus this plus this, you get this. You add this plus this plus this plus this, you get this. And then you add all of these, you get 1. Maybe you find that easier. But any which way, that's the way we find the cumulative probabilities. Sometimes it's very useful because we say cumulative probability of 25 megawatt or more out of service. What is that? 25 megawatt or more out. capacity outage, 25 megawatt or 50 out or 75 out or 75 or 100 out. Instead of adding all these, you just look at this number. You know what I'm trying to say? If I want to know the cumulative probability of 25 megawatt or more out of service, then all I need to look at is this particular row here, 0.039, instead of saying, oh, probability of 25 out is this, 50 out is this, 75 out is this, therefore I must add these four numbers. But I've already done that here. So it's kind of useful, the cumulative probability of X megawatt or more out of service. Okay. So this is our famous or infamous capacity outage probability table. As you can see, the cumulative probability value decreases as the capacity on outage increases. So capacity on outage is increasing, but what is happening to the cumulative probability? It's always going down. Yeah. This has to be true. Yeah. Whereas for individual probabilities, also generally the same trend is there, but there may be some states which have a higher probability compared to something lower down in the table. So we cannot say for the state probability, but cumulative probability guaranteed. It will always go from 1 and keep reducing. Yeah. Now we have this table. I gave you an example of 4 generators. We have 5 states. Suppose there are 40 generators. Suppose you have 40 generators, 2 to the power 40. So my capacity outage probability table will be huge. Of course, you can argue we have the computational facilities. Yeah, we can always write a small computer program and get that capacity outage table. But you looked at some of the values here. 1 into 10 to the power minus 8. Is this a meaningful number? Can I not ignore it? Can I not say, oh, okay, I have this capacity table which has hundreds of states. Suppose I stop and draw a line somewhere and I say, okay, if any probability is below 10 to the power minus 6, I'm going to ignore it. So I truncate the table, right? So I use that as one of the approximate methods. Yeah. So we use truncated tables by omitting all the capacity outages for which the cumulative probability less than a certain value. You can choose that, 10 to the power minus 8, 10 to the power minus 6, or whatever. So that's called truncation. There is another method to reduce the capacity outage probability table, that's called as the rounding approach. So for example, if your table has 3 megawatt unit, 5 megawatt unit, 10 megawatt unit. So you've got capacity outage states 0, 3, 5, 8, 13, and so on, right? Maybe I put all of these states into bands. So for example, I say that the band is 5 megawatt. So the first one I will say 0 to 5 megawatt. The next one I'll say 5 to 10 megawatt. Next one I'll say 10 to 15 megawatt. That helps me to reduce the number of entries in the table when I band them together within a certain band, which could be 3 megawatt, 5 megawatt, 10 megawatt, depending upon the sizes of units in your system. It's not a one size fits all. So that's the second method that is used in the literature. It's called as a rounding approach. But the truncation approach is obviously simpler, because all you do is, once your cumulative probability hits a certain value, once your cumulative probability hits this value, below this all the values will be even smaller. I just now told you that cumulative probability will always start from 1 and will always reduce. So once you hit this value, you say, oh, I'm not going to go below this at all. I'm going to draw a line. That's it. This is my capacity outage probability table. Okay. Right. Now what happens when the units are non-identical? We just saw a case where the units were identical. We were able to use the binomial distribution. Sorry, what is the time? I just need to, is it 12:30? 25. 12:52. Oh, but I'm sure you are willing to stay on, right? Yeah, not a problem. I have seen that from day one. You're very keen, so let's not worry. Yeah, we'll try to finish it by 1:15, but if it goes beyond that, I'm sure you will be eager to stay on, just like I am. So where was I? I lost my train of thoughts. Yeah, so we were talking about these two approximations. One is the rounding and the other is the truncation. One is banding by rounding off, and the other is truncation below a certain value, typically 1 times 10 to the power minus 8. So now the units are non-identical. What should we do? We cannot use the binomial distribution anymore, but we can simply use the methods of probability. The methods of probability will be very similar to the binomial, but just not using binomial. So I use an example to illustrate. Consider a 4 generating unit system with an installed capacity of 100 megawatt, consisting of 140 megawatt, 4% forced outage rate unit, and 320 megawatt, 4% forced outage rate units. Obtain the capacity model in the form of a COPT, okay? So what can we do here? We still have 3 generators which are identical, right? 3 generators are identical, same capacity, same unavailability. So we can still use the binomial for these 3, correct? We can still use the binomial for these 3 generators, right? So that's what we'll do. First combine the 3 units using binomial, and then find the table for this unit. What's the table for this unit? State 1, capacity outage 0. State 2, capacity outage 40. What is the probability of state 1? Capacity outage 0. It is 0.96, right? And the state 2, 0.04. So you've got 2 tables. And now we all know from mathematics how to combine. That's why on the first day I went through the rules of probability. If the events are independent, the events are dependent, how do we combine them, right? So all that comes to our rescue. So this table shows you the capacity outage probability table for the 3 20 megawatt generators which are identical. The forced outage rate is 0.04, so I can get this using the binomial distribution, right? The second table here is for the single generating unit, 40 megawatt generating unit, which can exist in 2 states. 0 capacity out, 0.96, 40 out, 0.04. So how do I get the eventual capacity outage probability table? Well, let me, what we call, enumerate all the possibilities. So I call this state A, B, C, D, E, F, G, H, I. Capacity available. So suppose the maximum capacity available here is 60. So here is 40. So if I'm in this state for this generators, and I'm in this state for this generators, the total available capacity is 60 plus 40. Is it not? And if I'm in this state for this table, but I'm in this state for this table, the capacity available is 60 plus 0. But what about the probability? Capacity is very easy, add the 2. What about the probability? If I am in this state for the first table and I am in this state for the second table, then the total capacity available is 60 plus 40. But what is the total probability? Do you add them? These are independent outages, remember. So probability of A times probability of B. So that's what we do. How do we obtain? Table 1, the first one, A, table 1, yeah, the first one. So you multiply the 2, you will get this probability. So that's what I have shown you here. How do we obtain the different values? 3A, 2B, 4A, 1B, yeah, where 4 here refers to this 4, yeah, and 1 and 2 is B. So this is B, this is A, okay? Correct? Are you with me? So when I say 4A, I'm referring to this state. When I say 2B, I'm referring to this state, right? So these are states from B. These are states from A, okay? So that's what it is, 3A, 2B, 4A, 1B, okay? You can get all those probabilities, independent events. But you observe here, capacity out, 40, 20. So you don't expect them to fall like ascending or descending. They will fall all over the place. So we need to combine some of these so that we have a unique order. We can't have, 20 out, 40 out first and then 20 out. That's not the way we order the capacity outage probability table. It must go from 0 to 20 to 40 to 60 and so on and so forth. Can't be 0, 40, 20. You can't have those kinds of states in between. So I'm going to reorder this. I notice that there is 140 here, another 40 here. So how should I combine the probabilities now? How should I combine the probabilities now? Yes? Add them. Very good. Yeah, you can add them. Yeah. So that's what we have done. Yeah. How we have obtained. I have also put those steps here from these states, and you can get the individual state probability, and then you can get the cumulative probability. Again, these calculations can be done very easily because we've got only 4 generators. If I've got 100 generators, there is just no way. You need a computer program, right? Yeah. So now we come to this recursive algorithm. Okay, we can do binomial, we can use non-binomial for small systems, but what if the system has hundreds of generators? We need something more. So that's why this recursive algorithm was developed to obtain the COPT. It can have any number of generators, and you can program this recursive algorithm very easily. So this recursive algorithm, we start with the 2-state first, and then we'll go on to the multi-state, okay? So obviously we want to start with the simpler case rather than the more difficult case. So the recursive algorithm goes like this. Capital P is cumulative probability, please, you remember that, right? Small p is state probability, uppercase P is cumulative probability. So cumulative probability of capacity on outage being X after a unit is added. After a unit is added to the system. So in other words, we will add units one at a time. Initially we'll say the system doesn't have anything. So I'll add the first unit, then I'll add the second unit, then I'll add the third unit. You can also use this algorithm to remove a unit. You can also use this algorithm to maintain a unit. So this algorithm is very versatile. You can use it for additions, you can use it for removals and things like that. So the cumulative probability of capacity outage state of X megawatt after a unit of capacity C and forced outage rate U is added. Okay, so what is P prime of X here? P prime of X, unfortunately it is split over 2 slides, is the cumulative probability of capacity outage before the unit is added. So we need to know what is the probability of that state before adding this unit, okay? And what is Px is the cumulative probability after a unit is added. So one is before, the other is after. Now when you are adding the first unit and perhaps even subsequent units, you need to have some initial values, isn't it? I'm adding the first unit, I'm using an equation like this. So P prime of X minus C, suppose I'm adding the first unit. Let's say the first unit is 20 megawatt. Okay. So X unit outage. So what are the outage states? Assuming the unit is existing in 2 states. So X can have value 0 megawatt or 20 megawatt, right? I mean, what is the capacity on outage? Either 0 or 20, right? So let's say 0. So cumulative probability 0 is equal to availability times P prime of 0. What is P prime of 0? I don't have a previous state because I'm adding the first generator, right? So we need to initialize. That's why we use some initial values. So these are the initial values. P prime of X is equal to 1 for X less than or equal to 0. Or it is 0 if that is not the case. Meaning if X is greater than 0 and you don't have it in the previous step, then it will be 0. So this is how the recursive algorithm equation goes. Obviously, when we look at an example, we will understand it better. Okay. So let's look at the example. Please feel free to interject, or if you don't understand, I'm happy to repeat. But this is one of the very interesting and key algorithms for generation model building. So we use it on a 100 megawatt system with the following data. 320 megawatt units, lambda is given, mu is given, and 140 megawatt unit, lambda and mu happen to be the same. So makes it a little bit easier, I guess. Consider also that the 20 megawatt units are loaded first, followed by the 40 megawatt unit. Obviously, you got to decide the loading sequence. Which generator are you going to load first, then second, then third, and so on. So let's do it. So we are given lambda and mu, and it happens to be the same for all the generators, so we can find the availability and unavailability, right? We know how to calculate that. Availability is mu over lambda plus mu. Unavailability is the complement of that. We are assuming that the unit is existing only in 2 states. When we come to 3 states later, we'll see a slightly different calculation. So the COPT is created using the recursive algorithm. Step 1, at the first unit. So what are the values that X can take? Remember what is X in the equation? Capacity on outage. So when you add the first generator, the X value can be either 0 megawatt out or 20 megawatt out, correct? Only 2 possibilities are there. So we will have 2 rows of calculations. So what is the cumulative probability of 0 megawatt or more out of service? You remember the table a short while ago, I told you that the cumulative probability of 0 more out of service is always 1. You can do the calculation, you will get 1, but you know that it will be 1, correct? Anyway, let's look at the calculation using the equation. So what is this? Availability. Unfortunately, the equation is way back. So availability times P prime of X. That means P prime of 0. We don't have the table before this. So P prime of 0, we have to use the initial condition. What is P prime of 0? For X less than or equal to 0, it is 1. So for us, P prime of 0 is 1, correct? So I'm going to put that as 1. Plus unavailability multiplied by P prime of X minus C. P prime of X minus C. Now our X is 0. And what is our C? It's a 20 megawatt generator. So 0 minus 20 minus 20. And remember the initial condition again, X less than or equal to 0, it is 1. So therefore, this is 1. Okay, everybody with me? I know it's getting close to lunchtime, but yeah, if you can bear with me for a short while, we can finish this. But if you're not ready, we can quit, because this is quite involved. Okay? Yeah. No, I intended to continue. So, okay, step 1 done, right? Step 2. Now we add the second generator, which is also 20 megawatt. Yeah, and of course the lambda and mu are the same, availability and unavailability is the same. So what are the values that X can take now? Remember, now there are 2 generators in the system, each 20 megawatt, each can exist in 2 states. So what are the possible outage states, outage capacity states? 0 megawatt out, 20 megawatt out, or 40 megawatt out, right? When both the generators are out, you are losing 40. When any one of them is out, you are losing 20. And if nothing is out, then you are not losing anything. So we have 3 states, 0, 20, 40. For 0, it will always be 1. You can check it out. For P20, it is availability of this generator that we are adding, which happens to be 0.96, times P prime of 20. P prime of 20. This value you have to get from the previous step. This value you must get from the previous step. So it is 0.04, okay? Plus the unavailability times P prime of X minus C. X is 20, C is also 20, P prime of 0, you must go back to the initial condition, right? Yeah? When this is 0, then P prime is 1. Clear? So this becomes 1. Then 40, availability of the generator times P prime of 40. P prime of 40, go back to the previous step. I don't have a state 40. So therefore, I must go back to the initial condition. So initial condition says if X is greater than 0, then P prime is 0. So I'm going to substitute 0 there, right? Clear? Plus the unavailability times P prime of X minus C. X is 40, C is 20. So 40 minus 20 is 20. P prime of 20, is there a state? Yes, 0.04. So I'm going to put that value and then I get this, okay? This is how the recursive algorithm works. Let me show you one more step. Yeah, one more step, third unit. Now what is the value X can take? 0, 20, 40 and 60, right? So we'll start again, 20. Let's go to 20. Availability of the generator multiplied by P prime of X, P prime of 20. So we'll get the value from the previous step, 0.0784. Only the previous step can be used in the calculations, not the previous. Yeah, only one step beyond or one step before. Then unavailability times P prime of X minus C. X is 20, C is 40. Sorry, C is also 20. 20 minus 20 is 0. P prime of 0 according to initial conditions is 1. Okay, so that's what it is. So we start, we load first the 12 megawatt unit. Yeah, first 12 megawatt unit, the availability is 0.99, unavailability is 0.01. Cell खत्म हो गया, मेरा cell खत्म नहीं हुआ आपका. Are we too far out because they didn't plan for me to continue for so long? Maybe you just finish this example and stop it. I have the derated state example after. We'll need another 15 minutes, so maybe too much. Lag gaya cell sahab? Okay. So where was I? Yeah. Step 1, probability of 0 is 1. I'm not doing it. You can calculate if you like. It will always be 1. Then the next step is 12. X is 12. Availability times P prime of 12. I don't have anything before, so P prime of 12 will be 0. Plus unavailability times P prime of X minus C. 12 minus 12, 0. And P prime of 0 is 1. Correct? So I get this value. You expect this value, don't you? Because this generator has only 2 states. It is either available or not available. The cumulative probability here is 1. The cumulative probability here has to be 1 minus 0.99. Has to be 0.01. I mean, if you think out loud, you will see that that number has to be there. If you get anything else, then you are wrong. Correct? Next step, we add the second 12 megawatt unit. So what values can X take now? 0, 12 or 24, correct? So now P0 we assume, P12. Availability of this generator times P prime of 12. P prime of 12 I have, plus unavailability times P prime of X minus C. 12 minus 12, 0, which is 1, correct? And then next step, 24. Availability times P prime of 24, I don't have, so 0, plus unavailability times P prime of X minus C. 24 minus 12, 12. P prime of 12 is 0.01, correct? So all that is nice. Now we will see the interesting thing. So step 3, now you add the 20 megawatt unit. So what values can X take? 0, 12, 20, 24, 44, right? Combination of the 12s and the 20, right? So all these values X can take. So that's why we have all these values here. 12, 20, 24, 32 and 44. So the first one, find 12, availability times P prime of 12. P prime of 12 from the previous table, I have that number, okay? Plus unavailability times P prime of X minus C, 12 minus 20. So negative value is always equal to 1, right? For P prime of X minus C, if it is less than 0, then the probability is 1. Then go to 20, next one. Availability times P prime of 20. Now, I don't have a P prime of 20 in the previous step. Does it mean that I can put it as 0 or 1? The answer is no. So this is where we say that P prime of 20 is the same as P prime of 24, the next higher value than 20. Because this is the cumulative probability, must remember. 24 will include 20, right? Therefore, we go to the next step. So I'm going to use this probability, 0.0001. Okay? Plus the unavailability times P prime of X minus C, 20 minus 20. So that's always 1. Then let's go to the next step, 24. Availability times P prime of X, P prime of 24, which we have, yeah? Plus the unavailability times P prime of X minus C. 24 minus 20 is 4. So go back to the previous step. Do I have a 4? I don't have a 4, but the next step is 12. So that's 0.0199. So that's the number. So I'm sure now you can see the trend, and there is an exercise for your doing pleasure as always. I don't know who's going to help you this afternoon, but good luck to him or her. Okay, so we are going to stop here. I know that I need another 15-20 minutes for the derated states, but probably we can stop here. You guys must be hungry. I'm okay, but yeah, I think it's, to be fair to everybody, perhaps we stop here. Ma'am, is that okay? Yeah, thank you. Thank you very much for lending me your ears. Yeah, I'll see you tomorrow. Okay, all right, good morning again, ladies and gentlemen. So yesterday we were talking about generating capacity reliability evaluation. We started to talk about the generation model in the form of a capacity outage probability table. It's a simple table showing the capacity states and their corresponding probabilities. So it's as simple as that. We also said that instead of using state probabilities, we can use cumulative probabilities, and that is sometimes advantageous because we can directly find the cumulative probability of X or more megawatt out of service by just looking at one value rather than adding up a few values. Yeah. So we spoke about that. We looked at a few examples, and there were some exercises for your doing pleasure. And hopefully you are, up to speed with respect to what we have done. So we talked about binomial distribution first, and then we said, okay, maybe the components or the generating units are not identical, then you can't use binomial. So I gave you an example of that as well. And then we said that, okay, generators need not exist in two states all the time. So how do we model three-state units? So that's the one that we want to talk about today. Before we look at the calculation of the risk. Remember when we started with the generating capacity reliability evaluation, we said that we need the capacity model, we need the load model, and then we are going to convolve the two to get the risk model. So we are going to approach in that direction after completing this last aspect from this particular chapter, chapter number 6. Okay? Any questions so far? I usually ask for questions, comments, brickbats, as well as bouquets. You can throw anything at me. Okay? So multi-state unit representation. You look at that equation, the cumulative probability, uppercase P is cumulative, remember? Lowercase p is state probability. So uppercase P of the capacity outage state X, which may be 0 megawatt, 20 megawatt, 40 megawatt, whatever, is given by summation of the probability multiplied by P prime of X minus Ci. So there is a Pi and there is a Ci, and I is going from 1 to n. Now suppose we go back to the two-state unit for argument's sake, then it will be I equal to 1 to 2, correct? And then we'll have P1, P prime X minus C1 plus P2, P prime X minus C2, am I right? Imagine that the generator exists in two states, 0 megawatt out and 20 megawatt out. And the probability of 0 megawatt out is 0.99 and the probability of 20 megawatt out is 0.01. Availability and unavailability, correct? So what will this equation boil down to? 0.99 multiplied by P prime of X minus 0 plus 0.01 P prime of X minus 20, correct? Is it not the same as what we have learnt yesterday? So this equation actually reduces to what we have seen yesterday for a two-state unit. So now we are generalizing it. You can have any number of states of a particular generator. It could go from 1 to n. But typically we use, as I have been saying, 3 states at most, yeah, typically. Doesn't mean that you can't include more. As long as you have the data, why not? The basic problem is that we don't have the data. And then you don't have the data, you just pick some numbers from thin air, you are going to get thin air. Garbage in will be garbage out, right? As I said yesterday. So this is the equation that we need to now use, where Ci is the capacity outage state of unit that we are adding, right? So let's go back to this example 6.4, and I'm going to change the 4th unit. Yeah, the 4th generator. We are not going to change the first 3 generators, and that is advantageous to us. Why? Then I'm building the capacity table, right? I add one unit, then I add the second unit, then I add the third unit. So I don't have to change those three tables. That's the advantage. If I put this as the first unit, everything will change, even though the end result will be the same. So the loading order does not affect the COPT, capacity outage probability table, but the way we are building it, the answers, intermediate answers will be different, right? So in order to save us that time and effort, I'm not changing the first three generators from this example, but I'm changing the fourth generator, the 40 megawatt unit, and instead of the 40 megawatt generator being existing in 2 states, now I'm saying that it can exist in 3 states. So the state is I, the capacity outage is CI, and the probability of that capacity outage is PI. Clear? Those are the things that we will need for this equation. Yeah, the small PI, state probability, the small CI, capacity of that particular state being out. Okay. So since the first 3 units, the 20 megawatt units of that example are still the same, no change. So therefore steps 1, 2 and 3 will remain the same as before. It's only step 4 which will change. So what will step 4 look like? We now add the 4th unit. What values can X take? It's still the same, 0, 20, 40, 60 and 80, because even though this 4th generator can exist in 3 states, the values are all multiples of 20. So therefore it doesn't change anything. If I had said 0, 15, 40, then things will be different, right? So now it's 0, 20, 40. So everything is still a multiple of 20. So the first step will always give us 1. We spoke about this yesterday. Cumulative probability of 0 megawatt or more out of service will always be 1. You can test it out. Then cumulative probability of 20 is the probability of the first state. Here, go back again. Probability of the first state multiplied by P prime of X minus 0. Correct? Plus probability of the second state multiplied by P prime of X minus 20 plus 0.01 multiplied by P prime of X minus 40, right? So because I have to go back and forth in slides, so I'm just trying to put the things together, right? So that's what we have. 0.95 times P prime of X minus 0. The first one is X minus 0. What is the X that we are adding? Yeah, what is the X? We are adding 40 megawatt unit, correct? Correct? The unit capacity is 40. So 40 minus 0 is 40. So P prime of 40, we got to go back several steps later. Yeah, here. Step 3, P prime of 40. Is that the same question? Not sure. Yep, this is the question. I thought it was 6.4. Yeah, this one. Yeah, so from here, no. It's the previous one, this one, right? Yeah, so step 3. So P prime of 40 is 004672. Where am I now? Going back and forth. Sorry? No, here it is P20, right? Yeah, so X minus 20, so 40 minus 20 is 20, right? So that's correct. And then 0.04 times P prime of X minus, if you go back to this, X, yeah, this is 20, the second one. The first one is 0. Are we doing the right thing? I just want to make sure that the number is correct. Yeah, 0.115264. Step 3. P20, so P20 is PI, P prime of X minus CI, right? So X is 20, 20 minus 0 is 20, right? So 0.115 plus PI, P prime of X minus CI, 20 minus 20 is P prime of 0, which will be 1, plus 0.01 times P prime of X minus CI. CI is 40, So 20 minus 40 is minus 20, and that probability will always be 1. Okay. Then 40 is 0.95 times p prime of x minus 40 minus 0, 40. So that's the number coming from step number 3. And this number is coming from step number 3, 40 minus 20, and this number will be 1. So like that, you see that we can still calculate the capacity outage probability table. So it doesn't matter, you can include 3 steps, 4 steps, 5 steps, but the basic equation is the same, except that now we can generalize it in this particular form. Yeah. So it is actually the same equation that we used for a 2-state model as well.